On this item, we have a control arm that has a flexible rod that prevents this from rotating about our pin support at C. And we've got two different applied loads. Part A asks us to design the pin that is the connector of the flexible rod that's up here at point A, and then to select what that diameter would be to the nearest 1/4 inch. So we've got to figure out what the force is in the pin. We note from this diagram over here that the pin is in single shear, which means ultimately that whatever the shear force is that's going through the pin, it'll all entirely pass through one shear plane, the cross section of the pin itself. Right, so what we've got to do then is to go figure out what that force in the pin is. Here's our free body diagram. We do have to have the CX and the CY reactions shown in the free body diagram. If we don't, then what's going to happen is if we try to do sum of forces in the X or the Y, we're going to get it all messed up. We also need to note that the pin-pin nature of the rod AB means that AB is a two-force member. It has to have an axial force that is in line with the two connecting points, horizontal in this case. So there's our axial force that's going on. And again, looking ahead, whatever the axial force is in the member is going to be equal to the shear force that has to be transferred through the pin. And again, because there's only one shear plane, that means the shear in the pin is exactly equal to the axial force. So we spend moments about point C to find out that the axial force is 3. Note that we have to get the proper component of the force out here that's inclined. So, hey, you know, on a 3, 4, 5 kind of thing, the rise is only 3, the run is 4, so the vertical component, which is the perpendicular one to the moment arm, is going to be the smaller of either the 3/5 or the 4/5. Okay, so that's how we get the axial force. The limiting stress that we have is 12 KSI, but we seek to have at least a 1.5 factor safety. So the allowable has to be smaller than the limiting or the criterion stress. So allowable stress is 8 KSI. Simple direct shear, V over area of the pin, and that'd be the cross section of the pin, which would be a pi d squared over 4 term. So on and so forth. We end up with an absolute minimum diameter of 0.691. I don't know what the nearest 1/4 inch is overall, rounding up, rounding down, but hey, we can't have a smaller diameter or it won't be strong enough. So it's got to go up, in other words, to the nearest 1/4 inch. So we'll use a 3/4 inch pin for that connection. Right now, in the second item, we're asked to find the factor of safety in the rod itself with respect to yielding. So that means we've got to go look up for A36 material what the yield stress is, not the ultimate, because the specific criterion was associated with yielding. So we look that up. It turns out the number is the same as this A36 business, so it's 36 KSI from our reference sheet. The applied stress is an axial stress, so it's axial force over the cross-sectional area of the rod, which is a different diameter than the pin, so 3 kips over pi, and then the radius squared. So it's a 1/2 inch diameter, 1/4 inch radius, and we have a axial stress of 15.2 KSI, so 36 over the 15.28 is going to give us a factor of safety of about 2.4. And then the last part is to ask what's the displacement that's happening at A. The displacement, that means the movement of the control arm at point A. Right, the movement, not the deformation of it, because the point A does not deform. But that location is linked to the axial, well, it's linked to the rod, and the rod is connected to a point that does not displace, point B. So A is going to move exactly by the same amount that the rod is going to axially deform. And that's why then we see A delta A, the displacement of A is equal to axial deformation of this rod. That's modeled by NL over AE, and we've already calculated the stress, so I put it in terms of the N over A is right there. Right, so boom, put it all in, keep track of your units properly, and we have a displacement at A that is 0.0026 inches to the right. A very stiff system, right? These are pretty significant loads. I mean, shoot, on the whole system we have something like 8,000 pounds, and we get thousandths of an inch of displacement. Kind of interesting.